In Lesson 5, you'll review some types of word problems that you had in advanced mathematics, and these types of word problems will also be helpful for us in calculus as well. If you remember from Lesson 1, something I said about calculus is that calculus was devised to help us measure instantaneous rates of change. And so any problems dealing with rates would be helpful for us in our study of calculus. Word problems involve inductive, deductive reasoning, and analogous thinking. Those three types of reasoning skills are all applied in doing a word problem. In a word problem, we observe the problem and we try to come up with some kind of a rule or a formula, and that's what inductive reasoning is about. That formula is going to be analogous to the words that we just read in the problem. So there we use analogies, and then we use deductive reasoning by learning new truths based on different types of rules that we already know. The first thing we should always do in a word problem is read it through one time. Look for keywords as we read it. So let's read this. It says, James could clean 3 fishes every 2 minutes, and Peter could clean 7 fishes every 3 minutes. Working together, how long would it take them to clean 23 fishes? So we've read it through once, and some key words here are how long. That's helping us know what our question is. What are we trying to answer here? We are trying to find out how long. So we're trying to find a time, one value. That means we need one equation to solve this problem. If we can think of or come up with one equation that's analogous to these words, then we can solve this for the time it would take to clean 23 fishes. So think about what we have here. Think about James. He could clean 3 fish every 2 minutes. And if we multiply that by the number of minutes, let's just call that x minutes, the minutes units would cancel and we'd be left with fishes. So what we can do is set ourselves up an equation, 3 over 2 times the time, I'll just call that t, plus 7 over 3 times the time. The time's going to be the same for both of them. They're working the same amount of time. That's equal to 23 fishes. Maybe you're familiar with distance equals rate times time, that formula. Instead of distance here, we have fishes. Fishes equals a rate of fish per minute times a time of minutes. So we've come up with an analogous equation here based on the words in the problem. Now let's use deductive reasoning, or the rules that we know about, to solve this algebraic equation. Let's factor the t out, and we'd be left with 3/2 plus 7/3 is equal to 23. And we need a common denominator here, so that means if we multiply 3/2 by 3 over 3 and 7/3 by 2 over 2, we'll have 6's for our denominators. We'll end up with t times 9 plus 2 times 7 is 14. That would be 23 over 2 times 3 is 6. That equals 23. So t is equal to 6/23. We multiply both sides by 6/23 times 23. The 23's cancel and we get 6. Now remember, the units here were minutes. It would take 6 minutes for them to clean 23 fish. And actually plural for fish is fishes. We observed the problem and we came up with a rule that was analogous to the words in that problem. Then we used deductive reasoning. Applying algebraic rules, in this case, was our deductive reasoning process to find a new truth out. It takes 6 minutes for James and Peter working together to clean 23 fishes. All word problems can be solved by reading through them once, looking for keywords that help you answer the question, and determining just what that question is, and then make an equation or use some kind of formula to answer the question. Let's look at another rate type of problem here. And like we have said before, read through it once first. And let's read it. It says the time necessary to complete the project varied inversely with the number of engineers working on it and directly with the amount of money invested. When 5 engineers work and $2,000 is invested, the project takes 3 days. How long will it take to complete the project if 4 engineers work and $2,500 is invested? So look for some key words here. How long will it take? There's a key phrase. That's the question. We're trying to find how long it will take. So we're trying to find a time. We just have one unknown. So that means we can just set up one equation to solve this. Now think about it. The time necessary to complete the project varied inversely with the number of engineers and directly with the amount of money invested. So time, let's just say T for time, varied inversely with the number of engineers. So that would be like saying T times E. As time increased, the engineers decreased. That's what varied inversely means. As one goes up, the other goes down. What we need to assume here, since it didn't give us any different kinds of rates or anything, we'll assume that the rate is the same all the time for each group of time, engineers, and money invested. So time varies inversely with the number of engineers and directly with the amount of money invested. So that means time compared to the amount of money. So we'll just say M for money. Anytime you see vary directly, that implies a ratio. As one value increases, so does the other, or as one value goes down, so does the other. That means the ratio stays the same. So that's one thing we do on a problem like this where they don't tell us anything different, that we may have different rates going on. We assume that the time compared to the number of engineers and the amount of money, that ratio is constant. And what we can do is just say initially T1, E1, and M1, those initial values will equal some final values for time, number of engineers, and money. That product or ratio there, T, E over M, that's going to stay constant. And so we can set this initial set of conditions equal to the final set of conditions. And so varied inversely, varied directly, those names or those key phrases, those kind of gave it away that we were dealing with a rate problem here. And something's going to vary directly. That means that there's going to be a ratio there, and that ratio is going to stay constant. Varied inversely means a product stays constant. When one goes up, the other goes down, but the product of the two stays constant. Now, let's just think about it. We've come up with a formula here based on what we've observed in this problem, and when 5 engineers work and 2,000 is invested, the project takes 3 days. So those are our initial conditions, and we can just go ahead and substitute in 3 days for time, 5 engineers, over $2,000 for the money. That's equal to, when we have T2, we're trying to find that. So how long will it take? We're solving for T2 when there are 4 engineers and 2,500 invested. Now we can simplify a little bit here. 5 over 2,000 would just be 1 over 400. And then 4 over 2,500, that's the same thing as 1 over 625. So now we have 625 times 3, just cross multiply is what I'm doing here. 625 times 3 is equal to 400 T2. Divide both sides by 400, and actually we didn't need to do that 400 times T2 cross multiplication. We could have just left that alone. And now we just simplify that. And we can just say T2 will round to one decimal place, 4.7 days. It would take 4.7 days to complete the project, assuming that rate is constant, if you had 4 engineers and 2,500 invested. Now think about whether that answer made sense or not. The time necessary to complete the project varied inversely with the number of engineers working on it. So that means as the number of engineers decreased, like it did in this case, went from 5 to 4, the time would increase, because as one goes down, the other goes up. Our time did increase, that makes sense. And then it varies directly with the amount of money invested. So as the amount of money invested increases, the time has to increase as well in order for that ratio to stay constant. And so again, that says our time should increase, and it did. We had 4.7 days, so that does make sense. That helps us understand that our answer made sense there. There's really no way to check our work on a problem like this because we don't have any original equations. It's not like we're solving a system of equations here. We had to create our own equation that was analogous to the words in the problem. But we can think about what the problem means, and that gives us confidence as to whether the value we have for an answer is correct or not. Look at this problem. Let's read it through one time. The cost of a fishing reel varies linearly with the number of bearings it has. A reel with 1 bearing costs $20, and a reel with 5 bearings costs $95. How much does a reel with 4 bearings cost? Well, let's just think about what we're trying to do here. We're trying to find the cost of a reel. So we need one equation because we have one unknown. How much does the reel cost? So we know that the cost of a fishing reel varies linearly. So there's a key phrase, varies linearly. That should make us think of the equation of a line. And if we have 2 points, we can determine a line, right? The cost varies linearly. So that kind of means the cost depends on the number of bearings. And just make a little Cartesian coordinate system here real quick. Cost varies linearly with bearings. Cost equals m times the bearings plus the y-intercept. Instead of y equals mx plus b, we can say that y equals, or cost equals, m times bearings plus b, the y-intercept. We know 2 points here. Basically, we know a cost-bearing pair and then another cost-bearing pair. So we could figure out this equation of a line. Then we can substitute 4 bearings in to determine the cost. So let's just go ahead and do that. Let's think about our points here. Our x is bearings, so we have 1 bearing costing $20. So there's 1 point, basically, if we're thinking of a Cartesian coordinate system. And then we have 5, 95. So our slope, m, is our change in cost, which would be 75, over our change in bearings, which is 4. And we can just say cost is equal to 75 over 4 times the number of bearings plus b, the y-intercept. To find the y-intercept, let's just substitute 1, 20 in. When the cost is 20, we'd have 75 over 4 times 1, or just 75 over 4 plus b. Think about it. Subtract 75 over 4 from both sides. And that would cancel there. 20, we could multiply that by 4 over 4 to get 80 over 4 minus 75 over 4 is 5 over 4. So we end up with the cost being equal to 75 over 4 times the number of bearings plus 5 over 4. Now, when there are 4 bearings, the cost would just be C for cost is equal to 75 over 4 times 4 plus 5 over 4. The 4's cancel, and we end up with 75 plus 5 fourths, which is just 76 and a quarter, or $76.25. Now think about it. Does that make sense? When we had one bearing, it was $20. When we had 5, it was $95. We're wanting to know the cost when there's 4 bearings in the fishing reel, and that's less. Our value that we had was less than 95, but it's kind of close to 95. So I mean, that makes sense. We would expect our answer to be less than, but fairly close to $95. A key phrase there was varies linearly. So that kind of gave it away. We could make an equation of a line. Plus, we could kind of see that we had 2 points there in terms of bearings and cost. Takes 2 points to make a line. We wrote down our formula for the equation of a line in terms of cost and bearings, found the slope, found the y-intercept, found the missing cost relative to 4 bearings. Working with linear equations is going to be a really important thing to be able to do well in calculus. Let's go ahead and do one more problem. Let's read this one through. At noon, the floodgates were opened and they were closed when the big hand and little hand of the clock made a 270-degree angle. What time was it when the floodgates were closed? Well, let's just think about it. Think about a clock, and we'll use some observation here to help us think about the problem or do some pictures to make an analogous situation. At noon, the floodgates were open, so we have a big hand and a little hand that are right on top of each other. Then the floodgates were closed when they were 270 degrees apart. So basically, just think about it, the little hand, the hour hand, will have moved some, and then the big hand moved around to right here. If that's 90 right there, this would be 270 degrees around. Basically 45 minutes later. The way I like to do these problems is think of them as distance equals rate times time problems. And in Algebra 2 you did lots of distance formula problems. And think about it, just draw like 2 bars to represent starting and stopping. Floodgates opened, floodgates closed. At the beginning, the big hand and little hand were lined up. Then the little hand starts moving ahead, or the big hand, actually the big hand's going to move a lot farther, so we'll say this is the distance the big hand traveled. The little hand, you know, it doesn't move near as much. It only moves like 5 minute spaces in 1 hour. Whereas the big hand moves 1 minute space every minute. So the little hand doesn't move very far, but that distance that little hand did move plus 45 is equal to the distance that the big hand moved. So in order for them to be 270 degrees or 45 minutes apart, the big hand would have to move 45 minutes or 45 spaces basically, plus a little bit more because the little hand moved some as well. Now we could just say DL plus 45 is equal to the distance the big hand moved. Our question is, what time was it when the floodgates were closed? Well, we're trying to solve for time here. We know that distance equals rate times time. We can rearrange this and solve it in terms of time. Both of the big hand and the little hand are obviously moving for the same amount of time. So our times would be equal. TL is equal to TB. Let's just rearrange this equation or rewrite it in terms of rates and times. We could say rate of the little hand times time. Since the times are equal, we don't need a subscript. Plus 45 is equal to rate of the big hand times time. So to solve for time, we still need to figure out the rate of the little hand and the big hand. The rate of the big hand, it basically moves 1 space every minute. And so we could just say 1 for its rate. The little hand, think about that, it moves 5 spaces an hour. or 5 spaces every 60 minutes, or 1 space every 12 minutes. So we're doing things in terms of spaces per minute here. So the time that we're going to find for this problem will be the time in minutes. We can add that to noon to figure out what time it was when the floodgates were closed. So let's go ahead and substitute what we know into our rate equation. The rate of the little hand is 1/12 times the time plus 45 is equal to the rate of the big hand, which is 1 times time. Subtract 1/12 t from both sides and you end up with 45 is equal to 11 t over 12. Multiply both sides by 12 over 11. T is equal to 45 times 12 over 11. And so that's equal to 540 over 11. And we can just write that as a mixed number, 49 and 1/11. So our time, therefore, would just be 12, 49, and 1/11 minutes, we could say. So think about it. Does that make sense? Well, when the big hand and the little hand are at a 270-degree angle, that would be 45 minutes apart, or 12:45, but that little hand has moved some as well, so we have to add that in to our 45 minutes apart, and that makes sense that our answer is a little bit bigger than 12:45. You can solve all these clock problems using this distance equals rate times time format here. Since it's a clock, the rates are always going to be the same. The big hand will be 1 space a minute, the little hand will be a 1/12 of a space per minute. And usually these problems are dealing with the big hand relative to the little one, some angle or some minute amount apart. Always keep in mind that that little hand is also moving a little bit as the big hand moves as well. Okay, well that's all for lesson 5.